Hi, in this video we're going to be doing a weak acid and strong base titration problem. So first they told us that we have this much HC2H3O2 and then we're adding strong base to it. So to calculate the initial pH, which is before any NaOH is added, and this will just be 50.0. And now to calculate the initial pH before any NaOH is added, we're just going to create a simple rise chart of the weak acid HC2H3O2 and then use the original concentration that we're given, which is 0.100 molar. And then we plus H2O. This will form C2H3O2 minus plus H3O plus. Because we only have the acetic acid, we won't have any of these to start with, and process out minus X, 0.1 minus X, plus X, X, and X. Now, what is the Ka for HC2H3O2? The Ka is 1.8 times 10 to the negative fifth. So 1.8 times 10 to the negative fifth. So to produce H2O plus, we don't use Kb or anything. So just do 1.8 times 10 to the negative fifth is equal to x squared divided by 0.1. Because our K is so small, we can remove this minus x. So 1.8 e to the negative fifth times 0.1, and take the square root of that. It will give us x of 0.00134. Now we take that and take the negative log of that, negative log of x to get our pH. Negative log that, and our pH will be 2.87. And let's see how many sig figs we're supposed to do. We have 3 significant figures, so let's run through 3 significant figures. It'll be 2.872. And for pH, remember, you only count the significant figures after the decimal point. So this is our pH of initial of only the HC2H3O2 in the solution. Now we start adding base. So first, to calculate 5 milliliters of NaOH, right? We have 1 liter per 1,000 milliliters. And what's the molar concentration for NaOH? It's 0.1 molar. So 0.1 moles per 1 liter. So it's 5 times 0.1 divided by 1,000. You'll get 5 times 10 to the negative fourth. Now we need to calculate the moles for acetic acid. So acetic acid, we said we have 0.005. So we don't need to calculate anything for that. So 0.125 moles. Let's write it in scientific notation. 1, 2, 3. So 5 times 10 to the negative 3 moles. Now to show the consumption of the NaOH, we need to create an RBCA chart. RBCA chart is moles. So C2H3O2. This time we won't be adding water. We'll be adding OH minus to it. Na is a weak conjugate acid of a strong base, so it's going to be spec'd around. And now let's create this into, this will donate a proton, so it will be C2H3O2 minus plus water. And now before the reaction begins, we have 5.0 times 10 to the negative 4, and this is NaOH. And this is acetic acid. So this will be 5.0, 5 times 10 to the negative third. It will be 5 times 10 to the negative fourth. It will be 0, and cross this out. Minus a smaller number, which is 5 times 10 to the negative fourth. So 5 e to the negative third minus 5 e to the negative fourth will give you 0.0045. This will be plus 5 times 10 to the negative fourth. That'll give you 0.0. No, this will just give you 5 times 10 to the negative fourth. Now let's convert these back to molar, alright? So if we're going to convert this back to molar, we're going to divide this by, let's see, 50 milliliters plus another 5 milliliters. So it's going to be 55 milliliters. Divide by 0.055 and divide this by 0.055. So 0.0045 divided by 0.055 can give you 0.018. This 5 e to the negative fourth divided by 0.055 will give you 0.00909. Now our HH equation. So HH equation says pH is equal to pKa times the log of conjugate base on top and the acid on the bottom, and because we're producing, let me write the equation real quick. Right, so now we have all the OH minus used up, so we can use, to find the pH, we can use this equation. We can use our HC2H3O2 again. HC2H3O2 plus normal water and forms C2H3O2 minus plus H3O plus. Because we're producing H3O plus, we're going to use this equation. In the next video, I'm going to show you an example where we do not produce H3O plus and instead produce OH minus. And this is when we use the opposite of this, where POH is equal to the pKb plus the log of conjugate acid on top and base on bottom. So now we produce H3O plus, so we're going to, this is the equation that we're going to be using. Alright, now let me teach you another trick. Alright, so we have pH equals pKa times the log of conjugate base divided by an acid, right? And these are concentrations. But if you look over here, so we're doing, first of all, you know that we are in the same solution, right? We're adding NaOH into HC to H3O2, and they're in the same beaker. So now that they're in the same solution, the volume is going to stay constant, which is why we're dividing both of these by the same number, 0.055 and 0.055. So when you divide both of these by 0.55, that means the ratio between these two numbers stay the same. So technically, when we're using our HH equation, we can continue to use the moles that we have. So pH is actually pK. What's pK? pK is negative log of our K, which is 1.8 times 10 to the negative 5th. 1.8 to the negative 5th, which can be 4.74. Now, times the log, you can choose to use moles. If you want to skip the step of converting to molar, you can choose to use moles. So what is going to be on top? You can choose to choose to continue using moles. So on top we're going to have 0.0, no, on top we're going to have the conjugate base. So 5.0 times 10 to the negative 4 divided by 0.0045. Again, we do not have to divide this. If we're going to divide this by, let's see, 0.055, right? And divide this by 0.055. What's going to happen? These two are going to cancel each other out. So technically, it should be the same thing. So if you don't want to convert into molars, as long as they're in the same solution, you don't have to convert to molars. So let's keep using the moles. Let's cross both of these out. So 4.74 plus the log of 5.0 e to the negative 4th on top and 0.0045 on the bottom will give you a pH of 3.786. Now, if you were to divide these by 0.55, plug in your calculator and you're going to arrive as the same answer. Now, it might be a little bit off depending on how much you round. So, in fact, if you don't include this, your answer is only going to be more accurate. Okay, now let's continue. We have 25 milliliters this time. 25 ml, same process, 1 liter, 1,000 milliliters. And then we have 0.1 moles, our molar did not change, and 1 liter on the bottom. 25 times 0.1 divided by 1,000 is going to give you 0.0025. Oh wait, no, actually we don't even need all this. If we do the RBCA chart, because we're at half equivalence point, what happens at half equivalence point? pH equals pKa. So what is our pKa? 4.74. So our pH is going to be 4.74. It's that easy. We don't need to show any work. We just need to state that at half equivalence point, pH equals pKa, and pKa is 4.74 as we found over here. So pH is going to be 4.74. Now let's quickly take the negative log of that because we need 3 sig figs. So negative log of what is our K? 1.8 e to the negative 5th is going to be 4.745. So that is our pH. pH equals pKa, which is 4.745. Now we add 40 milliliters. All right. So this time, let's try adding 40 milliliters. 1 liter, 1,000 milliliters. 0.1 moles, 1 liter. 40 divided by 1,000 times 0.1. It will be 0.004. This will be 0.005. So I'm going to do RBCA chart. It's going to be on top, what is it? HC2H3O2 plus our strong base forms C2H3O2 minus C2H3O2 minus plus H2O. This is going to be 0.005. This is going to be 0.004. And now this is going to be 0, and we're going to cross it out. Minus 0.004 plus 0.004. It's going to be 0.001, and this is going to be 0.004. Now we just straight up use the pH equals pKa plus the log of conjugate base divided by acid. So pH is equal to 4.74 plus the log of 0.004 divided by 0.001. 4.74 plus the log of 0.004 divided by 0.001 gives you 5.35. pH is 5.34. Next, 49 milliliters. 49 milliliters, 1 liter. 49 divided by 1000 times 0.1. 1 liter is going to be 0.0049, and this is still 0.005. So RBCA would be HC2 H3O2 plus 8OH minus makes C2H3O2 minus plus H2O. 0.005 is going to be 0.0049 divided with minus 0.0049 on both sides, is going to be 0.0001. Yeah. Alright, this is going to be plus, this is going to be 0 over here, plus 0.0049, is 0.0049. So pH is going to be equal to 4.74 plus the log of conjugate base, which is 0.0499, 0.0049, divided by acid, which is 0.0001. So 14 plus the log 4.74 plus the log of 0.0049 divided by 0.030 and another 1. It's going to be pH of 6.430. And the previous one is 5.342 when drawn through these three significant figures. Alright. And finally add 49.95. So 49.95 divided by 1000 times 0.1 is going to be 0.004995. RBCA. Right now, I'm going to start simplifying HAC instead of HC2H3O2 minus HC2H3O2. Now, on the AP exam, you cannot simplify it like this. But for the purpose of the video, I'm going to simplify acetic acid to AC and simplify acetic ion to AC minus. Plus OH minus forms AC minus plus H2O. Now this is going to be 0.001, this is going to be 0.00, no, this is going to be 0.05, sorry, 0.4995 minus 0.004995, this equals 0, and this equals 0.005 minus 0.004995. It's going to be 5 times 10 to the negative 6th power. This is plus 0.004995, this is 0.004995. So our pH is going to be equal to 4.74 plus the log of 0.4995 divided by 0.0001. No, shoot, sorry. Divided by 5 times 10 to the negative 6. So same equation, 4.74 plus 4995 on top, and on the bottom, 5.0 e to the negative 6. Which will give you 7.739, 7.740. Next, we have 50 milliliters. So 50 is going to be equivalence point. Now, how will this work at equivalence point? H, RBCA, HAC plus OH minus produces AC minus plus H2O. Now, this, whatever, I'm not going to worry about what's in here, what's in the before, because after, it's all going to turn into 0. Now, AC minus, we start off with 0. And now, what is the amount of moles? So over here, I told you we have 0.005 moles. So when we have 50 milliliters, it's also going to be 0.005. So we're going to plus 0.005. And these two are, this number is going to be over here as well. For both of HAC and this one is going to be minus 0.005. Anyways, now plus 0.005. And now, let's see, we are out of HAC and out of OH minus. So now we actually need to create a new rice chart. And before we do that, we need to convert this back into molar. So what is our volume? Our volume is 100 milliliters divided by, because we added 50 milliliters and we have 50 milliliters from the beginning. So 0.1. 0.005 divided by 0.1. It can be 0.5. 0.05. So now we're going to do AC minus plus H2O our only solution left plus water, which will form, this will donate it to. So HC2H3O2 plus OH minus. Alright, so this is going to be AC minus, and this water is going to be donating a proton. So AC minus will be 0.05. It's going to be, cross it out, be 0, 0, plus X, it's going to be X, it's going to be minus X, minus X, and 0.05 minus X. Now, we need to use the KB of AC minus. So what is KB? We're going to use 1.0 e to the negative 14th divided by our Ka, which is 1.8 times 10 to the negative 5th, which will give you 5.56 is times 10 to the negative 10th power is equal to x squared divided by 0.05. Now you do 5.56 e to the negative 10th times 0.05 and take the square root of that, which will give you pH of, no, POH, sorry, because we're using KB, right? It's going to be POH of 5.2726. Now we do 14 minus that number, and that's 1 to 366. Oh shoot. Sorry, this is going to be X value. X is going to be 5.273 times 10 to the negative 6 power. We take the 14 plus log of that. 14 plus log of X, because this is POH, it's going to be 8.722. Alright, now, and the reason we didn't use the HH equation because we can't. Alright, over here we have no HAC. So if we want to use the HH equation and divide it by acid on the bottom, we'll be dividing by 0, which is why we aren't able to do that. Okay, so now this one we have 50.05. So 50.05 divided by 1000 times 0.1 is going to give you 0.005 double 05, and this is going to be moles. So RBCA, and then we have HAC plus OH minus again, forming AC minus plus H2O. This would be 0.005, and this would be 0.005005. This would be 0, and this would be minus 0.005. It would be plus 0.005. This is going to be 0. Notice how this, our acid is now our limiting reactant, leaving us most of LH minus left. So 0.005005 minus 0.005 is going to give you 5 times 10 to the negative 6. Now we do not need to do the right chart or the HH equation anymore because we have most of OH minus. All we should do is divide this by the total volume, and that will give us a molar. Now with molar, we can find pH. So this divided by the total volume, let's see what this will be. Volume is going to be this milliliters plus the milliliters in the beginning, which should be 50 milliliters. So we have 50 milliliters plus 50, 0.05. So it'll be 100.05. It'll be 0.1005 liters. So 5.0 times e to the negative 6 divided by 0.1005 liters is going to give you 4.975 times 10 to the negative 5th. Now this is going to be 14 plus the log of X, because remember, this is OH concentration of OH minus, so it'll give us POH, so we're going to have to add 14 to it. Now 14 plus log of X, 14 plus log of X is going to give you 9.69. 9.697. Alright, finally, we have 51 milliliters. So this would be 0.0051 RBCA. HAC plus OH minus forms AC minus plus H2O. And you can, by the way, on this step where you just take the moles of acid or base depending on what you're adding, can only work when you have an excess of the base or acid you're adding. Otherwise, you're gonna have to do the Rice-Short or the HH equation using the acid and the conjugate base. Alright, so now it's gonna be still our concentration of our most of acetic acid never changed, so it's still gonna be 0.005. Plus this time will be 0.0051. minus 0.005 on both sides. It's going to be this is going to be 0, and this side is going to be 0.0001. AC is going to be 0 plus 0.005, but that's not really important anymore because we'll just be using this. Right now, 0.0001 divided by our new volume, which is 0.151 milliliters plus 50 milliliters, so which is 101. So 0.0001 divided by 0.101 is going to give you 9.901 times 10 to the negative fourth power. Now you do 14 plus the log of that. 14 plus log of that number is going to give you 10.995, which would be 11.000, and that is. And basically, to summarize, if you have an excess of OH or H2O plus, you can simply divide it by the volume to get the molar, and then when you have molar, you can find it by taking the negative log of it or 14 plus the log of it, and that gives you the pH. So yeah, when there's excess, it makes our work really easy. So let's look what happens. As we add more base, our pH increases, goes from 2.8 to 3.7 to 4.75, 4.74. Does that make sense? Yes, that does make sense because the more base we add, the higher our pH goes. So let's see, when we add 0 milliliters of NaOH, our pH is 2.872. So let's draw this over here, 2.872. When we have 0, it's going to be about here. Alright, when we add 10 milliliters, now when we add 5 milliliters, we have 3.786. So when we add 5, it's going to be about here. And when we add 25, it's going to be 4.745. 25 is going to be 4.745. About here. So you can be a little bit lower. About here. And then we add 49, which can be 6.4 now. At 49, it will be 6.4. And then this one is 7.74, but we don't really need to draw it because this is only like what 0.95 milliliters of difference. So we can keep that there. And now when we add 50, it goes to 9.69. So 50 is going to go up here. And when we add 51, it's going to turn to 11. So it's going to be here. So this is how our titration curve is going to look like. And yeah, that is our titration curve, and this is how our weak acid and strong base titration curve will look like. I know the drawing's not the best, but if it had more guidelines, maybe I could draw the line better. But you kind of get the idea. As we add in the beginning, this is our buffer area. All right. As we add more NaOH, our pH doesn't change by as much. But after our buffer is exceeded, the pH increases rapidly. And this is it for titration of weak acid with a strong base. Thank you for watching.